giving me the opportunity. Yeah, thank you for giving me the opportunity to present this work. So the first slide. Okay, here's the first slide. So the problem is very simple to describe, and yet has many applications, which is why some significant effort has been dedicated to it. So we wish to estimate probabilities of this form, which is essentially the probability that a multivariate student distributed random variable lies in some rectangle. Now here, here I use the fact that you have a mixture representation of the multivariate student. You can represent it as a scaled multivariate Gaussian divided by some chi-square scaling variable. Okay, so this is our first problem. We want to estimate this probability. And as I said, I deliberately keep the mixture, scale mixture representation of the student because it helps with the analysis and construction of the algorithm. Okay, so the first goal is to estimate this L, and the second goal is to simulate this random variable X over R, the student random variable, the multivariate student variable, conditional on lying in this set. We try to do this either approximately or where possible exactly. And this is not an easy problem because simple rejection sampling, naive rejection sampling, where we simulate X over R until it lies in the required set, is a rare event. It happens with a very small probability in high dimensions. Okay, so sampling from this multivariate student, which also includes the case, obviously, for multivariate Gaussian when the degrees of freedom is infinity, is equivalent to simulating from this density F, where the density, it's a joint density between R, the scaling variable, and Z, where Z, you can think of it as the multivariate Gaussian variable. So here I have applied a transformation. Transformation is that the covariance structure is in the constraints. So this matrix L, typically it is something like a Cholesky decomposition of the covariance matrix sigma. So it is a lower triangular matrix. So this matrix L is derived from sigma. It's not always necessarily a Cholesky factor, but let's assume it is a Cholesky factor. So it is either a lower or upper triangular matrix. And because of this structure, Professor Alan Gentz, who's an American statistician, he proposed a long time ago, he proposed the following decomposition of this region over which we have to integrate. Because L has a lower triangular structure, the region, oops, I don't know why I keep moving this. The region can be decomposed in this way. So basically start with Z1. Z1 is in this region using the fact that L is lower triangular. Then you can find bounds for Z2 given Z1 and so on until you get to ZD. So ZD lies in some range given Z1 up to ZD minus 1. So all of this just exploits the lower triangular structure. So on top of this, one way to construct an estimator for our quantity using this decomposition is to think of an important sampling estimator. So basically, The naive simulation involves standard Gaussian and a chi-square distribution, but we're going to simulate under a different measure, a different density. And that density will be inspired by the idea of Alan Gentz, which is that we have this sequential decomposition of the region. So our importance sampling density will have this sequential decomposition. First, we sample R, then we sample Z1 given R, then we sample ZD given R, Z1 up to ZD minus 1, and so on. By the way, feel free to interrupt me if there's something unclear. You can ask questions during the talk. Okay, so the methods that have been used thus far will not have any parameters, freely floating parameters, which need to be optimized. So I guess the novel idea here is that what we propose is using an importance sampling density, which is parameterized by some parameters, and these parameters can be chosen in a way that make the importance sampling estimator very efficient. So the scaling factor R is simulated from a truncated normal, and everything else is also simulated from a truncated normal, where we have, well, for each truncated normal, we have a different mean. And the simulation is sequential. So ZK is simulated conditional on R, Z1 up to ZK minus 1. And all of this conditioning is based on these intervals that we described here. Okay, so how do we choose these parameters? If we look at the likelihood ratio or log likelihood ratio, let's call it psi, our choice of the parameters is to basically choose the parameters so that the worst performance is minimized. It's like a minimax criterion. So the estimator based on a single sample is just this one. So we simulate the scale under a different measure. We simulate Z under a measure other than the standard Gaussian. So it's some kind of bizarre measure where each of these is a truncated Gaussian with different mean. So this is what the importance sampling estimator looks like. And the one thing that we have to determine is these parameters eta and nu. And our choice is going to minimize the worst possible behavior of the likelihood ratio. And one motivation, one reason for this is that this kind of worst kind of behavior puts an upper bound on the variance of the estimator. So we may not be able to directly estimate the variance, but we can calculate the worst case upper bound on the variance, and we can minimize this. And because this is a minimax problem, it can be solved by finding a saddle point. In other words, set all the gradients to 0 and solve the equations. So if I use this kind of method to select my importance sampling parameters, I get these optimal parameters mu star and eta star. So I can estimate the L, the probability of interest, and I can also use the rejection sampling algorithm for this truncated multivariate student. Now the rejection sampling is, there's nothing special about this. We simply use our importance sampling density as a proposal density in plain, simple rejection sampling algorithm. So I'll talk about this later, but surprisingly, this simple algorithm can work satisfactorily even for hundreds of dimensions. That's only because we have chosen these parameters very carefully. So in what sense are these parameters mu star and eta star optimal? So for importance sampling estimators, where you have a rare event, you have these concepts of efficiency. So you have the weakest possible efficiency is asymptotic or weak efficiency, which basically says that, well, it is this condition here. So I'm not going to explain more about this condition because we are in this talk, we have the strong efficiency. So strong efficiency simply means that the relative error of the estimator is bounded with respect to the rarity parameter. So relative error here is the variance over the quantity that we try to estimate squared. So this thing is bounded. It doesn't blow up to infinity. And if we're lucky enough, this constant here, C2, can be 0, in which case we have an even stronger condition, which is a vanishing relative error estimator. That's the best we can hope for. So our estimator, under certain conditions, is a bounded relative error estimator. So what this means is that if I try to estimate the probability that a multivariate student vector with a certain covariance matrix exceeds a threshold L, where L satisfies certain conditions, these asymptotic conditions are parameterized by gamma. So gamma is some kind of rarity parameter. Then I have a bounded relative error. So I guess the simplest manifestation of this is to take L is just a vector of constant, say 1, and multiply it by gamma, and gamma goes to infinity. Then obviously L times gamma divided by gamma will be a constant. So this condition is, for example, satisfied. Yeah, a simple application of this is to try to estimate the probability mass in the tails of a multivariate student distribution. And we can estimate this reliably, even in the even very small, astronomically small probabilities. So in previous work, actually, when the degrees of freedom go to infinity, we can show that the relative error goes to 0. So we have a vanishing relative error estimator. So here's a numerical example of the benefits of using the traditional estimator versus the importance sampling estimator. So here by the Gens estimator, I mean an estimator in which these mu star and eta star are, well, mu star is arbitrarily set to 0. Basically, the Gens estimator corresponds to not doing any change in the mean. So mu star is 0. And this R is simply simulated from the chi-square distribution. It doesn't have a different distribution. So you can see, I don't spend time describing the particular details of the example. This can be read in the paper. If you're interested, I can give you the paper with all the gruesome details. So this is just to illustrate the fact that without importance sampling, we can only estimate these probabilities accurately for something like 10 dimensions. And beyond, for higher than 10 dimensions, we lose accuracy. You know, we can be pretty confident that this is the true answer, whereas this one is already being quite inaccurate. And for say 30 dimensions, it's a no contest. So here, this in the brackets is actually the estimated relative error, and this relative error can be estimated without Monte Carlo. It can be, I can simply report this upper bound. So I have a deterministic bound which can be computed. And so I can be pretty confident that this answer is accurate. Whereas these answers are completely, if you don't use importance sampling, then you get meaningless answers. So the error is just too large. Okay, so what I would like to mention is that in order to prove this theorem, it was a very nice thing to discover a generalization of Mills ratio for multivariate student densities, which I could not find in the literature. So, the fact that I couldn't find it doesn't mean it's new. So I'm not gonna make claims that it's a novel result, but if somebody can point me to a reference, I'll be grateful. So what is Mills ratio? Everybody knows that the tail of the normal distribution asymptotically behaves like the normal density divided by gamma here, where gamma goes to infinity. So this result was generalized in the multivariate case by these famous researchers. So, for example, they derived the asymptotic distribution of the multivariate Gaussian tail, where y is multivariate Gaussian, and the formula looks like this. So the formula is very similar to the one-dimensional formula. So the multivariate Gaussian tail is asymptotically similar to the multivariate Gaussian density divided by some constants here. Now these things are determined by the active constraints of a quadratic programming problem. So I'm not going to go into the details of that, but the point is that the multivariate formula is very similar in structure to the univariate formula. And not surprisingly, in my paper, the Mills ratio for the multivariate student also looks very similar to the Mills ratio for the multivariate Gaussian. So the tail of the multivariate Gaussian, student density looks is asymptotically the same as the multivariate student density, where note that this sigma 1,1 is a subblock, a submatrix of the covariance matrix of the multivariate student. So it is not the entire matrix. It is just the subblock that will give us active constraints in a certain quadratic programming problem. And there's this constant C, which is not available analytically, but can be given by this integral. But it is a constant that does not depend on the asymptotic. So, and I believe it can be easily estimated by a Monte Carlo simulation. So anyway, that's kind of an interesting side result. The referees for the paper said, surely this must be known and must have been done before, but they did not provide me with any references. They just assumed that it must be done, but they couldn't point out to this result being published before. Okay, so now we move on to the next bit. How do we simulate conditional on a rare event? So remember, we proposed something like naive rejection sampling. So this is rejection sampling where we just use the importance sampling density. We calculate a likelihood ratio, compare it with some uniform, or if we do the log likelihood ratio, we compare it with an exponential variable. And if a condition is satisfied, then we get an exact draw. Now, the question is, what are the properties of the acceptance probability of this algorithm? How good is this algorithm when we try to simulate conditional on a rare event? So let me see. So there are a number of issues here. So the first one is the dimensionality. As the dimensions increase, exact simulation becomes more and more difficult. And the second problem is, even if the dimension is fixed or may not be too large, we may still have problems sampling conditional on this event, because the event is a rare event. So the probability of this event happening is very small. So these are two different issues, and but they kind of they are separate, but they interact. So here, the way I deal with high dimensionality is, okay, I give up on rejection sampling. I'm going to use Markov chain Monte Carlo. But the naive Markov chain Monte Carlo struggles to mix fast or to sample accurately when the event is rare. So somehow we need to characterize the efficiency of Markov chain Monte Carlo when the goal is to simulate a rare event. So Markov chain Monte Carlo may ultimately converge to the distribution conditional on the rare event, but this may happen very slowly, and it may be hampered by the rarity of the event. So here I propose a reject regenerate sampler. The justification for this idea is that if you apply rejection sampling and if it doesn't work, you just wasted a lot of time and simulation effort. And then you have to transition to Markov chain Monte Carlo. So wouldn't it be nice if, so yeah, for example, as I said, rejection sampling is efficient up to a certain dimension, and then we have to use MCMC because rejection sampling becomes inefficient in high dimensions. So as a user, you have to decide whether you want to transition from rejection sampling to regenerative sampling. You have to have a cutoff level. So this requires, the user to make a decision about which algorithm to use, and you're kind of wasting simulation effort. So why not have a single algorithm that will combine rejection sampling and MCMC in one single algorithm? So what is the idea of this algorithm? So the reject regenerate sampler simulates a random variable at each step, and with a certain probability, so this x of t is interpreted as a member of a Markov chain. So as a part of a Markov chain with stationary, with the required stationary distribution. However, with a certain probability, the Markov chain has a regenerative cycle. And some of these regenerative cycles could actually be, with a certain probability, could be pronounced to be exact or perfect draws. So in this way, if it is possible to make a perfect draw, we will be able to make it. And if it wasn't possible, then we'll simply be using the same simulation to run a Markov chain. And the user will not have to decide whether to choose between rejection sampling for exact simulation or MCMC. The two are combined seamlessly. So I can give you, the algorithm looks something like, given the current state of the Markov chain, you always keep another variable Bn, and this variable Bn, if it is 0, then this xn is interpreted as just an unremarkable state of a Markov chain. However, if Bn is 1, then we have a regenerative event. So it means that the Markov chain can be segmented into independent cycles. And that is very useful for, because we then have RID analysis. And if Bn is actually upgraded to 2, takes the value of 2, another event happens, then this xn is actually an exact draw from the target. So this is the advantage of this rejection regenerative sampling. And what can we say about the efficiency of such an algorithm when we have rare events? So for Markov chains, we can use the total variation distance to measure the the distance from the stationary distribution. And so let's take T, which is the number of steps required to bring the total variation distance below epsilon. Excuse me, some water. So what do I mean by a rare event efficiency concepts for Markov chain Monte Carlo? Well, I call a Markov chain Monte Carlo algorithm or sampler asymptotically efficient if as the event, as the rarity parameter goes to infinity, the number of Markov chain steps required to keep within a certain error, to keep the total variation distance below epsilon, if that doesn't grows only polynomially but not exponentially, then I have an asymptotically weakly efficient Markov chain. Now, if the number of Markov chain steps required to achieve a given precision is does not, it's bounded uniformly from above, then I have a strongly efficient chain. I should have put a constant here, perhaps. So in some sense, the accuracy of the Markov chain is not affected by the rarity of the event. All of these statements can also be made uniform by, I guess, making the total variation distance independent of the initial starting point of the chain. So anyway, so I think I described this. So the result is that for the multivariate student distribution, when we simulate conditional on a rare event, our reject regenerate algorithm using our important sampling density G as a proposal simulates in a strongly efficient Markov chain. So if I may not be able to deliver to you always, in many cases I can, but there's no a priori guarantee. I cannot deliver perfect draws from the multivariate student conditional on this event, but what I can deliver is a guarantee that the Markov chain algorithm is going to, it will not be affected by how rare this event is. Its mixing rate will not deteriorate as the event becomes more and more rare. Okay, so now this is important because if you don't take this into account, what you find is that as the event becomes more and more rare, the performance of the Markov chain deteriorates. Its mixing rate simply drops. So let me see how much time I have. Maybe I have examples, and maybe I can simply point you to the paper rather than covering these examples. So there are numerous examples from Bayesian statistics. So very briefly, I don't want to spend too much time on this, but say this is a Tobit model. So in a Tobit model, you may have the standard linear regression with a response variable, which is only observed if it is, for example, larger than 0. If it is below 0, then what you observe is just 0. So it's like censoring. And it's applied to, so the Bayesian posterior looks looks something like this. And so this is using real world data, real world example. And what is possible is that you can simulate perfectly from the posterior. So I didn't even have to use the Markov chain because the rejection sampling was already quite good. And so this is rejection sampling in extremely high dimensions. Let me see, the dimensions are, I believe that many dimensions. I should have checked. Anyway, it's written in the paper. So in any case, another example is if you want to simulate the stock price trajectory of a barrier option which is exercised. So with these barrier options, it will only be worth something is, for example, the stock price goes above a certain level, or maybe goes below a certain level and also above a certain level. And these, depending on the magnitude of these levels, this could be a rare event. You know, what's the probability that the Dow Jones on the US stock exchange is going to hit 100 within the next 12 months and go back to 40,000? I mean, that would be a very small probability. Whatever model you use, it should be an extremely small probability. That would be unthinkable. But the point is that we can simulate this, the trajectory of a stock price model under a Black-Scholes model. We can simulate this exactly. And here's a, let me see, here's the effect of, so we have an independent sampler which is optimized to be asymptotically efficient with respect to rare events, and a random walk which is not optimized. And the point here is that the independent sampler is performing better because it's optimized. So that's just to illustrate the value of having a strongly efficient Markov chain in the rare event sense. Okay, so I wanted to get to the interesting bit, which is always the stuff that I'm doing now or intend to do. So all of this now is work that has been done, and I can give you the paper. And this is current ongoing work, and I want to talk about it because it is quite interesting to me, and I hope you can be convinced that it is useful and interesting as well. So the problem with what we have described so far is that it only works when the dimension of the multivariate student or Gaussian is roughly less than 10 to the power of 4. So the algorithm that I have described here, basically, yeah, this estimator with this theoretical guarantee, it is the current state of the art as far as I'm aware. There is no other method that can give you such accuracy as given on this numerical example. However, it is the state of the art maybe only when the dimension is small to medium. Okay, so when the dimension is too large, where is it? Okay, it is here. When the dimension is, say, larger than 10,000, then it becomes very slow. It will still give you an answer, but you just have to wait and wait and wait. And yeah, people are not happy to wait for hours just to calculate the multivariate student quantity. And the bottleneck is essentially the cost of calculating a lower triangular matrix L, which is usually d cube. So if I have to factorize 10,000 by 10,000 covariance matrix, that's just ridiculously small, ridiculously slow. And that's one of the bottlenecks, I think the major one. So there you will, surprisingly, there are applications where the dimensions can be much larger than 10 to the power of 4. These include Gaussian graphical models and Gaussian random fields in which instead of working with the covariance matrix, you work with its inverse called the precision matrix. And if it's a Gaussian graphical model, then this precision matrix lambda will actually be quite sparse. And this sparsity may be exploited in various ways, either to do a sparse Cholesky decomposition or some kind of clever factorization. So in what I propose, we're going to assume that this matrix L has special structure which makes matrix vector multiplications very fast. So this could be the case when lambda, the precision matrix, is sparse, or it could be the case where the matrix is structured. For example, you can use fast Fourier transform to compute matrix vector products very quickly. Any structure that allows you to compute matrix vector products quickly can be exploited in this algorithm, because the algorithm only needs matrix vector products, nothing else. So what is the algorithm? When we deal with such high dimensions, d larger than 10 to the power of 4, it doesn't make sense to estimate the probability itself. You only can hope to estimate it on a logarithmic scale. So we should aim to estimate the logarithm of the probability. It will be something extremely small. And the idea is to write this quantity. So I'm looking at a Gaussian case. Obviously, the multivariate student will be similar. So the idea is to write this probability as an integral over a region and a log determinant. Now, this log determinant can be so this comes from simply the Gaussian, right? Here we have a multivariate Gaussian, and the multivariate Gaussian has the determinant of the precision matrix. So when I take a log, I get the log determinant, and here this integral is such that when you integrate this auxiliary variable v, I will get a Gaussian. I will get an exponential here. I'll get something that looks like the Gaussian density without its determinant, without this lambda. So the idea of the large-scale algorithm is to estimate the log determinant and this integral separately. Now, the log determinant, estimating a log determinant of a large matrix is a well-studied problem. There's something called stochastic Lankosh quadrature. You can see, for example, these papers here by Youssef Saad and so on. So this is a very common problem in machine learning, and I have nothing to contribute to it. So basically, I'm using the well-known stochastic Lankosh quadrature. It is very fast, works, you know, small Monte Carlo sample size gives you highly accurate results, and it takes a fraction of a second. And it allows you to approximate the log determinant of huge matrices. So this is what we use for the log determinant. So really the challenge is the second part. And so here's where there is some novelty. So the novelty is to use generalized splitting. Well, it's not surprising, since this is something I've been working on, and as Nadir mentioned at the beginning, I have proposed this method called generalized splitting. So it is not surprising that I opt to choose it in this work. But let me explain why I think it is a good method, and hopefully you're convinced. So this method, first of all, this method requires running a Markov chain Monte Carlo algorithm that will sample uniformly over this region. So this region incorporates the constraints that Z has to be between L and U, and also has this quadratic term which has to fall in some set. So this set is a convex set. It is the intersection of linear inequalities with a convex set, so it is also a convex set. So we need to sample uniformly on a convex set, and for this we're going to use some kind of Markov chain Monte Carlo, and I use hit and run sampling. So within splitting, I have to sample from densities which which look like this. So I need to be able to sample from uniformly on this region. And because there's research that shows that hit and run actually has polynomial mixing rate, as the dimensions become very large, the number of steps that I have to take to achieve a certain accuracy only grows polynomially, something like d to the power of 5. And so that's, doesn't mean that the MCMC will work perfectly, very well, but it simply means that it's not going to be exponentially bad. So this is some very old work from the 90s, showing that hit and run sampling on convex regions is a decent method. So the way I sample from this region using hit and run, I only require calculating so lambda times vector, where this vector is always uniformly distributed on a unit sphere. So basically, I only require matrix vector multiplications to run this algorithm. Nothing else is required. Everything else is really orders of magnitude cheaper. So it's not really, doesn't really require any discussion. What else can I say? So the advantage of something like splitting is that you get an estimate of the probability on a logarithmic scale. So with sequential Monte Carlo methods, which is generally, well, splitting is a special case of sequential Monte Carlo. So you get these probabilities represented as products. So on a logarithmic scale, you get the sum, and each one of these probabilities is not very small. So you represent a rare event probability as a product of reasonably large probabilities, and you estimate each one of these probabilities separately, so that if you just have a very convenient representation on a logarithmic scale. You don't have this with any other method, as far as I'm aware. If you use importance sampling, and yeah, you have to take a logarithm of special functions. Usually, it is not convenient. It is a nightmare. To give you an example, if you want to calculate the logarithm of the Gaussian tail, you can't simply calculate the Gaussian tail and then take a logarithm. That will give you disastrous numerical inaccuracy. You actually need a special function that will calculate the logarithm of the Q function, the tail function of the Gaussian. You have to study its analytical properties to come up with something that will give you reasonable answers. So the situation is even more dire in higher dimensions. And so being able to represent your probability easily on a logarithmic scale is a huge advantage. I think I'm running out of time, so we'll try to summarize what this work has been all about, and then I hope you have some questions. So what we have is an importance sampling estimator, which is robust to rare event effects. So it enjoys the bounded relative error property for rare event estimators. And so this can be used to estimate any multivariate student probabilities. And this is currently the best, most accurate method, as long as the dimension of the problem, the multivariate student, is not too large. So think about this as large than roughly 10,000. So the other problem is to simulate multivariate student problem conditional on student vector conditional on a rare event. I didn't spend time on this, but this has nice applications in Bayesian statistics, basically sampling from a number of different posteriors is equivalent to sampling from a multivariate student conditional on a rare event. So we have something called reject regenerate sampler. And it is shown to be strongly efficient as Markov chain Monte Carlo sampler. It is shown to be strongly efficient with respect to rare event effects, large deviation effects. And finally, I mentioned that we have a completely different, we propose a completely different algorithm for very large dimensions. So for very large dimensions, we don't use this important sampling that we use for small to medium dimensions. And we no longer have bounded relative error. All bets are off. It's simply a heuristic to get an answer, because just getting an answer in high dimensions is already challenging. Even if the answer is not very accurate, it's already challenging just to get an answer. Because in the talk I promised applications, and I seem to be doing well with time. Let me just quickly, so this is the paper which I can send to you if you're interested in. So the applications that arise is, for example, Bayesian applications to constrain linear regression. So you may have a linear regression model in which the coefficients have to satisfy certain inequalities. And there's a real world example with the yield of some apple trees. And the apple trees are of different age, and you expect that the older the tree, the higher the yield. And so you can incorporate this prior knowledge in your Bayesian model, and it will be incorporated as some sort of inequalities on the coefficients. And so this immediately means that you have to sample from a multivariate student conditional on some linear inequalities. So this is one example. A second example is the Tobit model I mentioned. And so a third example is Bayesian splines. So this means you may want to interpolate certain data, and you may want your interpolator to be non-negative. So these data could be quantities which we know cannot be negative. So your smoothing spline should not take negative values. This immediately imposes a set of linear constraints on your spline. And if the spline is modeled like a Kriging or a Gaussian process, then your posterior again will be a multivariate student truncated, a very high dimensional multivariate student truncated to some convex region described by linear inequalities. So these are three examples given in the paper, just to explain why this is a useful thing to have. Okay, so I think I will stop here, and hopefully let's see if you have any questions. Thank you very much for your time.